Dear students, welcome to Module 4, Session 3. In today's session, we are going to discuss about an important technique which is used to analyze the stability of the system. So in the previous session, we have discussed about RH stability analysis, where we used to consider the characteristic equation of the system, and using the characteristic equation, we used to construct a table called as RH table. So using the values in the table, we used to judge whether a system is stable or unstable by determining the number of sign changes in the first column. And based on the number of sign changes, we used to justify that the number of sign changes is nothing but equal to the number of the roots which lie in the right half of the S-plane. So the stability was just based on the location of your poles by taking the number of sign changes in the first column of roots array. But the main difficulty here was it was very difficult for us to determine at what point of time the system is going to become stable. For that purpose, to overcome that disadvantage, another technique is suggested, which is named as Rootlocus diagrams. So these are the diagrams which is constructed by tracing the movement of the roots on a particular axis in a particular direction. So the movement of the roots can be determined till infinity, and the stability can be analyzed in a proper way using Rootlocus diagrams. So this is the outline of my presentation today. So we'll be discussing about the basic concepts of Rootlocus. A brief introduction will be given to you regarding Rootlocus diagrams. Then we are going to study about conditions, that is angle and magnitude condition, which is used to judge the location of the Rootlocus, and we are going to study the different types of the rules for construction of the Rootlocus. Now coming to the introduction part. So when we consider a unity feedback control system, let's take the open loop transfer function as equal to k divided by s plus 1 with a feedback as equal to unity. So this is the basic closed loop control system what I am taking. Now for this particular closed loop system, the open loop transfer function is given as k divided by s plus 1. So this is our g of s. Okay, and the closed loop transfer function, as usual, we are going to determine it as equal to C of s by R of s, which is equal to G of s divided by 1 plus G of s. When you simplify this, we are going to get the transfer function as k divided by s plus 1 plus k. The one thing what we should know here is the open loop stability does not depend upon the gain value k in case of Rootlocus diagrams, and whereas the location of closed loop poles vary with the variation in the gain. Okay, now when we start varying the gain, so we are going to have different pole locations for different value of k. So here in the table, as you can see, we have taken different values for k. So we have to consider that the DC gain should be always greater than 0, because the gain is always considered to be a positive value. Now for k equal to 0.5, we are getting the pole location as equal to minus 1.5, and for 1 the pole location we are getting it as equal to minus 2, for 2 it is minus 3, and so on. So for different values of k, as you can observe, the pole locations are changing. Okay, so these are the location of the poles which is shown with the different colors here. So location at 0.5, at 1, 2, minus 3, minus 4, minus 6, minus 11, and minus 16 is shown here. So basically what it shows is the location of the poles, it basically depends upon the DC gain of the system. So we are starting from k equal to 0, and we can extend up to k equal to infinity also. So the Rootlocus is actually based on this concept only. We are defining the Rootlocus definition. The Rootlocus is the path of the roots of the characteristic equation traced out in the S-plane, as the system parameters like k varies from 0 to infinity. That was shown in the last slide. You could see how the location of the poles varies when we change the value of k from 0 to different values till up to infinity. So that is what is the definition of a Rootlocus. It is the path traced by the roots for the given characteristic equation. We have defined the Rootlocus as a path of roots of the characteristic equation traced out in the S-plane. as the system parameters varies from 0 to infinity. Right? This I've told you. Now coming to the next part. So here this was the open loop transfer function which we have taken, which is equal to k divided by s plus 1 plus k, and this table is already shared, and we have seen how the value of k affects the position of the poles, and you can see that your roots of the characteristic equation, which is nothing but the location of your poles, are changing as we change the value of k. So now let's see how to sketch the root locus. Okay, the first thing is we need to compute all the roots for the values of k. For example, if the closed loop transfer function C of s by R of s is equal to k divided by s into s plus 1 to s plus 10 into s plus 20 plus k. Now for the different values of k, we are supposed to evaluate the root locus location, and the first thing is we are supposed to find the roots of the characteristic equation. Now finding the roots of the characteristic equation of the degree higher than 3 is very difficult, okay, and we need always a computer solution for this. So for that purpose, a simple method for finding the roots of the characteristic equation was developed by W.R. Evans and is predominantly used in control engineering. Now this method, called as the root locus method, is one in which the roots of the characteristic equations are plotted for all the values of system parameters. Now the root locus corresponding to the particular value for a particular parameter can then be located on the resulting graph, and we have to note that the parameter usually it is considered as gain, but any other variable of the open loop transfer function can also be used for construction of the root locus. And by using the root locus method, the designer can predict the effects on the root locus of the closed loop poles of by varying the gain value or by adding open loop poles or open loop zeros. Now let's start with the first basic concepts of root locus diagram. So before starting the root locus diagram sketch, we need to verify two conditions, that is angle and magnitude condition. So in the construction of root locus, the angle and magnitude conditions are very much important. Now let's see how to verify these two conditions for a closed loop system with open loop transfer function as g of s and feedback as h of s. Now as you know, the closed loop transfer function C of s by R of s is given as g of s divided by 1 plus g of s into h of s, and the characteristic equation of the closed loop system is given as equal to 1 plus g of s into h of s is equal to 0. This is our characteristic equation. Now, or else you can rewrite this as equal to what? G of s into h of s is equal to minus 1. Now, here g of s into h of s is the ratio of polynomials in S, and since they are complex quantities, it can be split into angle and magnitude part. So the angle of this function is given as angle of g of s into h of s is equal to angle of minus 1, or g of s into h of s is taken as plus or minus 180 degree into 2k plus 1. So this condition is called as our angle condition for the root locus diagrams, where k can take the value as equal to 1, 2, 3 and so on. And the magnitude condition is taken as magnitude of g of s into h of s is equal to magnitude of 1, or the magnitude of g of s into h of s should be equal to 1. Now coming to these two conditions, that is angle condition and magnitude condition, this is named as the angle condition, that is the angle of g of s and h of s should be equal to plus or minus 180 degree into 2k plus 1, where k can take the values 1, 2, 3, and magnitude condition is taken as g of s into h of s is equal to 1. So the values of x that fulfills both the angle and magnitude conditions are the roots of the characteristic equation, or they are called as the closed loop poles. So they have to satisfy these two conditions. Then only they can be considered as the roots of the characteristic equation. And a locus of points in the complex plane satisfying the angle condition alone is the root locus. Okay, this is one thing what you need to remember. Now, to apply angle and magnitude conditions graphically, we must first draw poles and zeros of g of s into h of s in the S plane. For example, if g of s into h of s is given as s plus 1 divided by s into s plus 3 into s plus 4, then this is giving us location of what? Poles. This gives us location of poles, as you know, previously we have discussed, and s plus 1 gives the location of zeros. This gives us the location of zeros. So if we can observe here, we have poles, that is 3 poles. One pole is at the origin, another pole is at minus 3, one more pole is at minus 4. So 3 poles at s is equal to 0, minus 3 and minus 4, and we have a 0 at s is equal to minus 1. These are our poles which I am representing it as P, and these are our zeros which I am representing it by Z, right? Now, so we are just joining all the poles together and zeros, okay? Now, the angle theta 1 is nothing but the angle formed due to the pole at the location minus 4. We are representing the angle due to the pole at minus 3 as theta 2, and angle due to the 0 is represented as phi 1, and angle due to the pole at the origin is represented as theta 3. And angle of g of s, the angle condition for g of s into h of s is nothing but equal to, at s is equal to p, which is equal to phi 1, that is angle summation of all the angles due to 0, summation of zeros angle minus summation of poles angle. Okay, so which you can symbolically represent it as, if you want you can just write this as summation of phi z minus summation of, since we have represented as theta, you can take this as equal to theta p. This we are going to evaluate now. Okay, so here, if the angle of g of s into h of s at s is equal to p is equal to 180 degree into 2k plus, if it is a multiple of 180 degree, it could be either plus or minus. The point p is said to be a root of the characteristic equation, and it is said to be a point on the root locus. Now let's verify this. So same diagram I'm taking, okay, or another way is, this is one thing, by measuring the angle you can just determine. Another thing is, I'm just trying to find the length of this line with respect to the poles and zeros. I'm representing them as b1a, b2 and b3, and the magnitude condition here is determined by a rule like this, where it is taken as magnitude of g of s into h of s at p s is equal to p is taken as s plus 1, magnitude of s plus 1 at s is equal to p, magnitude of s at s equal to p, s plus 3 at s equal to p, and s plus 4 at s equal to p. Or else, in terms of scale, if you measure here the distances, then it is taken as a divided by b1, b2 and b3. So let's see how to determine this with an example in the next slide. Now, so here an example is given, and here it is, the task is what? Apply angle and magnitude conditions on the unity feedback system at some value of s. S is given as 0.25. Now this is the closed loop transfer function or a system we have, with open loop transfer function as k divided by s into s plus 1. Now, so let's start. So it's a unity feedback system. So g of s into h of s is nothing but equal to k divided by s into s plus 1 into s plus 2. The first thing is, I need to find out the angle for this. It is taken as angle of g of s into h of s is taken as angle of k minus angle of s minus angle of s plus 1 minus angle of s plus 2. and it should be a multiple of 180 degree as usual. This is the condition what we have, the angle condition that has to be satisfied. Okay, let's see how we will do this. Now we are going to determine the angle condition for given value of s as equal to minus 0.25. Now angle of k at minus 0.25, angle of s at minus 0.25, everything we need to determine. Okay, now if you can see, since k is a constant value, the phase value will be 0, so you can take this as equal to 0. Now we have taken s as equal to minus 0.5, so it is angle of minus 0.5, angle of minus 0.7 and angle of 1.75. So when you simplify this, we are going to get the angle as equal to minus 180 degree. Okay, and which is a multiple of 180 degree itself. So angle condition is satisfied. Now we have to satisfy the magnitude conditions. Now according to that, magnitude of g of s into h of s should be 1. So let's see how this works out. Okay, now s is taken as for magnitude condition. Angle condition is anyhow mapped. Now s we are taking it as equal to minus 0.25. Okay, but we do not know the value of k at that specific point. So we can use the magnitude condition to determine the value of gain at the point where s is equal to minus 0.25. Now let's start. So wherever we have s, we are replacing it with minus 0.25. So that when you simplify it, here we are going to get the values k divided by minus 0.25 plus 0.75 plus 1.75 is equal to 1. Or when you simplify this, you will get the value as equal to k divided by minus 0.3285 is equal to 1, or k after taking the magnitude is just taken as k divided by 0.328 is equal to 1, or k is taken as equal to 0.328. So this is the gain value what we are supposed to have to satisfy the magnitude condition. So I hope you have understood the angle and magnitude condition. So here an example is given. So the s value is given as minus 0.2 plus j 0.937. Another value of s what I've given is minus 1 plus j2. Now try to determine the value of k for these two values of s. So consider this as an homework and try to simplify. Now coming to the construction of root locus, first step is uh, here you are supposed to locate the open loop poles and zeros in the S-plane. Okay, that is the first step of root locus. You have to determine the number of poles and number of zeros, and you have to determine the location also. So as you can see here, as an example, we have taken the open loop transfer function with unity feedback as k divided by s into s plus 1 into s plus 2. So it indicates that you do not have any zero. There are three poles, one at s is equal to 0, another one at s is equal to 1, one more at s is equal to minus 2, which is shown here in the diagram. So we are marking the poles with the cross symbol. So this is the first step. Identify the number of poles and zeros. Now we have to determine the root locus. Okay, that is our second step. So according to the given rule, the root locus will exist on the real axis. Towards the right side of it, you should have odd number of poles and zeros. Okay, so if I take the angle condition, it is not getting satisfied. Okay, so for this I'm just verifying the angle condition. So here the angle condition, since it is not satisfying, there is no root locus on the positive real axis that we have determined. Okay, now we are supposed to check the point on the negative real axis between 0 to minus 1. I'm just taking this point to be P2, and now if you replace, okay, s value, we're going to get the angle as equal to minus 180 degree, and the angle condition gets satisfied. Okay, and based on this, one more point, I am taking the value between minus 1 and minus 2. For this value also I am getting the angle condition which is satisfied. So angle value here I am getting it as equal to minus 360 degrees. So this is also getting satisfied. This is just a verification. Okay. And now from minus 2 to minus infinity, uh, let's see, similarly here if we can see test points on the negative real axis between minus 2 satisfies the angle condition, and therefore your root locus exists here also. So when we are marking the root locus, here I have a root locus and here also I have a root locus. In between these two, since the angle condition is not satisfied between minus 1 minus 2, here I do not have a root locus. Or the simple way is, I'll tell you how to identify without any calculation. So just draw one arrow like this, see towards the right side. Okay, if you have odd number of poles and zeros towards the right side, okay, then you can mark the root locus here. Okay, and similarly come here, check between minus 1 and minus 2, put one arrow and refer to this side. Okay, if you refer towards this side, you can just count, you have 2 poles, so that means it is even. So in such cases I will not have any root locus, so here I am writing it as NRL, no root locus. Now similarly here, draw the arrow and refer towards this side. Okay, if I refer here from minus 2, you have odd number of poles, so you will have a root locus here and you have to highlight the root locus position. This is what is done. So just take your value between the two poles or zeros, whatever, and just see towards its right side and just check whether you have even or odd poles and zeros. If you have odd poles and zeros, then you will have a root locus. If you have even poles and zeros, then it is said to be no root locus. Now the next rule is determining the asymptotes of the root locus. Asymptotes are nothing but the straight lines or reference lines which are drawn to sketch the root locus. So your root locus is said to travel parallelly along with these asymptotes. Okay, so here we are supposed to determine two values for asymptotes, that is one value is called as the centroid value, another one is called as the angle of asymptote. Here sigma is called as your centroid, this is your centroid point, and psi is called as your angle of asymptote. So in different books different notations are used, so you do not have to worry, the formula remains the same, and this is called as your asymptotes. Okay, so this is your actual root locus curve, and asymptotes is nothing but indicated here in the blue color, which is taken as your approximate line, reference line for construction of root locus. And we have a formula which is used to determine the angle of asymptotes. So note down this formula. Angle of asymptotes is nothing but equal to plus or minus 180 degree into 2k plus 1 divided by n minus 1. So here n is taken as number of poles and m is taken as number of zeros. Now for the previous example what we have taken, if we try to find the angle of asymptotes and the uh, centroid point, the angle of asymptotes is taken as plus or minus 180 degree to k plus 1 divided by n minus 1 is number of poles was 3 and number of zeros is 0. So this is the angle of asymptotes what we are going to get, and by replacing the value of k as equal to 0, 1, 2 and 3, since I need to have 4 asymptotes. Okay, so we are getting here the value as equal to plus or minus 60 degree, plus or minus 180 degree, plus or minus 300 degree and plus or minus 420 degree. Actually you have to stop at this point itself, so do not take the fourth value, you can stop at the third value itself. Okay, so since this angle is getting repeated after 360 degree, you can neglect it and you can stop. So usually the hint is, so how much is your p minus z, those many angles you must determine. Since p minus z is equal to 3, number of poles minus number of zeros is equal to 3, so take only 3 angle values for asymptotes. So thus we are assuming the 3 angles to be 60 degree, minus 60 degree and 180 degree, or else it is nothing but taken as 60 degree. In terms of positive values, if you want to take it as 60 degree, 180 degree and 300 degree. Okay, now before we draw the asymptotes or the reference lines on our plot, we have to determine the centroid for the asymptotes. So the formula to determine the centroid for asymptotes is given as sigma poles minus sigma zeros divided by n minus 1. So you have to add all the values of poles and subtract with the sum of zeros, and that has to be divided by n minus 1, or it is taken as p minus z also in some of the books. For this example, what we have taken, we have poles at 0, minus 1 and minus 2. Summate it, we will get minus 3. So no 0, so it is minus 0 divided by p minus z or n minus m. It is nothing but equal to 3 minus 0. So we are getting the sigma value as equal to minus 3 by 3, or it is equal to minus 1. So this is the centroid value what we have got for the previous example. Now you have to plot this centroid by taking sigma as equal to minus 1. If you can see here, sigma is marked at minus 1, and we are first drawing the first asymptote, which is shown in red color with 60 degree or minus 60 degree. You can in turn take it as equal to 300 also, one and the same, and 180 degree. So these red lines what I have here, they are nothing but our asymptotes or reference lines for the construction of the Rootlocus. So I'm stopping at this point today. So there are further 5 more rules which we need to discuss in the next session. So that I'll start in the next session. So after learning all the rules, we will be moving to the construction of the Rootlocus. Please take this as an homework problem. So in today's session, we have discussed about the Rootlocus axis, real axis, the angle of asymptotes, and the centroid point that we are supposed to determine for the asymptote. So as a part of today's session, I am giving this as an assignment for you. So take the block diagram and try to determine the Rootlocus on the real axis, and also determine the angle of asymptotes and centroid. In today's session, we have discussed about Rootlocus diagrams, and the basic concepts of Rootlocus is discussed along with angle and magnitude conditions, followed by we have discussed about the 4 important tools that is used to check the position of the Rootlocus, and also we have learned how to determine the angle of asymptotes and the centroid value for the asymptotes for construction of the Rootlocus. I hope today's session was interesting. So these are the reference book from which I've taken the concepts, and you can also refer them. Thank you all. Have a nice day. Jai Shri Gurudev.